Okay. I think we've hit enough people to get started, because if any more people show up, we're going to have a serious problem. So, everybody come in. Okay. Those of you who don't know me, I'm AJ. That's my contact information. A bunch of you were at the first review. Most of you were not. So I've broken this test based on the one that I had last year and past ones that I've seen before into 3 topics: non-concurrent equilibrium, stress, and axial deformation. You guys come up with something else that you've kind of seen that you think you want me to take a look at, let me know. But I'm going to start with going through these. So I'll give a bit of a lesson on each of them and then do a practice problem as was. It's going to be the problem from my test last semester, or last year. So the first topic, which I've already set up, we're just going to get right into it, is non-concurrent equilibrium. There we go. Which you guys did concurrent equilibrium on the last test. Different than that, this just means that the forces don't meet at a point. So as opposed to that, which is concurrent, you now have some type of rigid body with a lot of weird stuff going on. That's the first of the 3 topics generalized. So to solve these problems, on the test, they're going to give you different types of supports. These are the 4 different types of supports they're going to give you, so I'm going to go through each one and what you have to know for each. And then when you actually go to solve the problems, if you see this support, you can convert it into the forces, and then you can solve the problems like force moment problems like in test 1. So going through the different types of supports, the first is rocker, roller, whatever you want to call it. I think most people call it a roller. This is the symbol for it, and you have one force going perpendicular to the plane of the roller. That's it. So when you solve for it, you only get one unknown. So if you see this symbol, or if they say in the problem there's a roller at point A, you have one unknown, and then when you get to the problem later, you can actually, you'll have to solve for AY at some point. The next type is smooth, which is essentially, you don't see this one very often, but it's the same exact thing as the roller. You have a point B, and you have a force that's going perpendicular to that point. So again, same as the rocker and roller, there's only one unknown. The third type, yeah, if you guys could find any, just whatever works. The third type is the pin or hinge. The symbol for this one is the triangle with these little fixed hash line thingies. I don't know. This one is going to have 2 reactions coming off of it. So this support will give you a reaction perpendicular. So if the beam itself is going this way, you have one going along it, and then one perpendicular to it, X and Y respectively, depending on how it's drawn. If the triangle's sideways, it'll be different. And remember, when you're taking calculations, you're taking it not from this like skewed off point that I drew. That's just to make it easier. You're taking it from that center point C that you're working at. And the fourth one is fixed. This one will give you 3 reactions from it. You're going to get dx and dy just like with the pin and hinge, but since it's fixed, you're also going to get a moment. So when you actually come around to solve for it, you're going to get 3 unknowns in your problem, which you're going to have to solve for. And like I said, this one is 2 unknowns. So before we get into a problem, does anyone have any questions on the supports, the reactions, the unknowns, what you're solving for, anything with this? Cool. So I'll do my test 1 problem from last year, which incorporates this stuff. That picture's not coming out so great. The rest of them will be better, so I'll draw this one by hand, so just give me a hot second. You can probably read the, yeah, you can still read the question, just the figure's a little crummy. Hey guys. Do me a favor and bear with my crummy drawing skills. I promise they won't get better as the day goes on. Okay, so from the wording of the question, that's close enough. At least you have a bigger idea of what's happening. A poorly mounted shelf supports an electrical motor which has a mass of, it's in my hand, 15 kilograms and a mass center at GM. So this is GM. The shelf has a mass of 4 kilograms and a mass center of GP, which is here. Assume that a single bolt B holds the shelf up and the bracket rests against the smooth wall at A. So the hints you get from that problem are, the standing out one is the word smooth at A. So that tells you here you have a smooth reaction, which I donate with like X's, close enough, as long as you make it apparent in your drawing. And the other idea you were supposed to get was that since this isn't put up, if a shelf was put up correctly, it would be fixed into the wall, which would give you 3 reaction forces from it. You'd have an X, a Y, and a moment. Since this was put up poorly, and picture a screw kind of going into the wall like that, it's no longer fixed and it becomes a pin because it can rotate essentially here if you were to actually push the shelf up onto the wall. So what you were supposed to get from the wording of the problem, and this is probably as tricky as it might get in terms of like the picture and the wording, is that the reaction at B is going to be a pin and a hinge. Does anyone have a question as to how I got those reactions? Sam?
Why isn't it a smooth?
A is a smooth. So A is a smooth because it says that it's against the smooth wall at A.
Okay.
So that's this bottom bracket on the shelf here. So A is smooth. And then B is pinned because the way I like to think about it is you'll get a reaction wherever you can't get easy displacement. So it can't shift up because the screw is still in the way. It can't shift to the right in the X direction because the screw is still in the way. But it has an ability to pivot here, which loses that moment. So this guy is still a pin. But again, if they had said it was put up correctly, this would be a fixed, and then you'd actually end up with 4 unknowns and you couldn't solve it. But they wouldn't do that to you. So is everybody good on that so far? Cool. So the first part of the problem was just to draw the free body diagram. So let me rephrase. The first part of the question is that they want the free body diagram of the shelf. So what I'm going to draw here is the shelf. So the forces you have are the force caused by the weight of the shelf itself, the cause force by the mass of the motor on the shelf, and then you get your reactions. So if you draw this down, and for the sake of this problem, they told us not to worry about the angle or anything because it was minimal enough that it just kind of went away. But we asked about that just to be safe. they're not going to make you worry about stuff like that. So at point B, you're going to have a pin. And then at point A, it's going to be smooth. So based on the way I said, based on the reactions you get from the supports, at the pin, you're going to get a reaction in the x direction, which we'll call A of x, and a reaction in the y direction, well, except it's B. I guess try to find a spot if you can. B of x and B of y. And now at the smooth connection, you're going to get a force perpendicular to where the bracket is touching the wall, which in this case, since we're treating as if it was upright, is going to be a horizontal force this way at A. Is everyone good so far? Does anyone have any questions on what I just drew? All good. So we know these values here, and we know all our distances. So according to the diagram, this is 200 millimeters. This is 150 millimeters. The distance from the center of mass of the motor to the shelf is 0.05 meters. The distance from the shelf to B is 0.04 meters. And the distance from B to A is 0.06 meters. On top of that, the mass of the motor is 15 kilograms. And the mass of the shelf is 4 kilograms. So this is part A. We have our free body diagram. That's all you need for that. You could add the values here before you actually get to solving. So the force here is 4 kilograms times 9.81 meters per second squared, which is 39.24 newtons. And this is 15 kilograms times 9.81 meters per second squared, which is 147.15 newtons. That 5. That's your free body diagram. Part B was to determine the reactions at A and B. So solve for these three forces. So this is bringing you back to test 1, where you have a force moment system and you get 3 equations because for non-concurrent equilibrium, instead of just f of x equals 0 and f of y equals 0, you also get the summation of a moment at any point is equal to 0, which are your 3 governing equations. Since you have 3 equations and only 3 unknowns, you can solve the rest for part B. So if we're going to get into the actual math, is everybody cool if I erase this left part over here? Everybody good? No complaints? Okay. Okay. So the first thing I did was I took the moment about B, because if you take the moment about any point, the forces that go through that point go away in that step. So if you take the moment through B, by goes away, bx goes away, and you only get to solve for ax, which makes that first step easier. So part B, the first equation, summation of moment around B. So for here, we have A of x is positive because it's going counterclockwise around point B. So you get positive A of x times the distance between the line of action of A of x, which is this, and point B, which is 0.06 meters. Minus 4 kilograms times 9.81 meters per second squared, because it's negative because it's going clockwise around, so just the positive negative sign of moments. So it's negative 39.24 newtons times the distance between that line of action and point B, which is 0.2 meters. And last step is minus 147.15 newtons times this 0.35 meters, because again, you're going clockwise, sign is negative, force times distance. And that's how you get your moment. So you'll all have calculators, do some math. A of x is equal to 989.2 newtons. And you're going to want to include what direction it's going in. So I originally denoted A of x as going to the right, and that's how I treated my signs when I plugged it into this equation. So since that was correct, and it came out positive, you're just going to agree that it is going to the right. And that's how you would notate it when you box your answer. Summation f, the next, it really doesn't matter which one you do next. I did summation fy next. So sum of the forces in the y direction is by, which I assume to be positive, minus 39.24 newtons, bless you, minus 147.15 newtons equals 0. By equals 186.39 newtons. Again, it was positive, so I know that it's still up. And the last equation that we haven't used yet, we used summation of moment. We used summation of fy, so now we use summation of fx, which is just A of x plus B of x equals 0. So we already saw for A of x, we know that it's 989.2 newtons. Plus B of x equals 0. So we get B of x equals negative 989.2 newtons. So now with this negative, since I assumed it to be to the right and it's the negative value of that, when I boxed my answer, I just put B of x equals 989.2 newtons to the left. And if at the beginning of the problem I had assumed that B of x is to the left and I had drawn the arrow like that and I had calculated all my moments assuming that this guy was going to the left, I would have gotten a positive value here, and then it would have agreed with that, and it still would have stayed to the left. So no matter which way you assume your vectors to be, you're going to get the same thing in the end as long as you follow the math through correctly. Does anyone have any questions on any of those steps I just did? Yes. Yes.
You start with a moment of B. A of x, why is this 6?
Say that again?
Like, a moment of B.
Yes.
You said x times 0.06.
Oh, okay. So moment is equal to force times distance, right? So we're looking at this force vector about B. So we know it's positive because if you take A of x, it's going to go counterclockwise about B. So that's the sign convention for that. A of x is the magnitude of the force, and 0.06 meters is the distance between between this line and B. All good? Everybody else good here? Awesome. That's non-concurrent equilibrium. So the next topic is stress. These are your two types of stress. You have normal stress, notated by sigma, which is the perpendicular force over the area, and shear stress, which is tau, which is the parallel force over the area. For a test problem, they're going to ask you for one or the other, so you're not going to have to sit there and guess what's what. But just so you kind of have an idea of what they look like, normal stress is when you're pulling along the length of something. So if this is your member, that is normal stress. Shear stress, tau, which is the other one, is if you're pulling against something. So here's a fixed support. One of the three reactions is this vertical force that comes up. So if you push a force up along something, that's shear stress. Those are the two different types. So depending on how the forces are acting on the body in whatever the problem you get is, you'll be able to figure out visually which one of those it is. But again, the problem's going to say something to the effect of calculate tau. So that's pretty much it. There's slight differences for when you calculate things. So when you actually get to the problems, the numbers are going to come out differently depending on when you have sigma or tau. And for when you have single and double shear, but we'll get into that as we do the problems because that's easier to see as you're solving it. So does anyone have any questions about the two types of stress? No. Awesome. So much better drawn than the other one. I don't actually have to draw this one. This is my problem 2 for my test last year. The steel pin at A is a diameter of 3/8 of an inch and is in double shear as shown. Determine the shear stress in the pin. So they told you in the problem, find tau, which makes your life a lot easier. They drew it out for you so you can kind of see exactly what they're talking about. This is A in double shear because the pin is on both sides. And then they just want you to find the stress in that point. So going through the problem step by step, we're going to start this just like everything else. Three-body diagram. So that guy up there, you get force B. It's cut off in this. You'll see it when I send the picture out later. I don't know why it got cut off. Basically, it's a piece of string connected to the ceiling. So there's a tension in that point. The top up there, it was called point D before it got cut off. So I notated this guy, force in BD. That's essentially what it breaks down to. This guy is 50 degrees. It gives you the 3.25 kips. Just as a reminder, a kip is 1,000 pounds if it becomes relevant. Inches. And they tell you in the question, determine the shear stress in the pin. So since you know it's a pin, or since they tell you it's a pin, that saves you some guessing. So from what we saw in the problem before, this pin at point A is going to give you two reactions. You're going to get one perpendicular. One parallel, I don't know, depends on reference, I guess. Those are your two reactions, and you also have your force in BD. So looking at the free body diagram, you can solve for each of those reaction forces. And then since the question is telling you to determine the shear stress in A, once you have the forces in A, you can solve for the stress using this equation. So doing this just very similar to the last problem, we're going to solve for the different forces. So the first thing we're going to do is we're actually going to break FBD up into its components. Yes. Where's what? The point D is like, it was cut off in this picture, but it's like right there. So the original picture was a piece of string connecting that. So calculating the force was just finding the tension in that piece of string. So the two components that you're going to get are going to be FBD Y and FBD X. FBD Y is just the force in BD times that sine of 50 because it's the vertical component of it. And FBDX is FBD times cosine 50 because it's adjacent. I'm sure you guys all have figured out trig by now. Oh, maybe not. That's the real trick. Okay, so these are your forces now. So the exact same trick that I did in the first problem, the first calculation I'm going to do out of summation fx, summation fy, and summation of a moment through a point is I'm going to take the moment through A because then both of these forces go away and we could solve for FBD in the first step. So summation of the moment at point A is FBD sine 50. It's counterclockwise, so it's positive. Times 16 inches, which is the distance horizontally across, plus FBD cosine 50 times the 20 inches. Minus, because it's clockwise, the 3.25 kips times the 44 inches, which is just 16 plus 28, which is the horizontal distance from A to C. Equals 0. Same thing, you only have one unknown. Do a little bit of algebra. It spits out the force in BD is equal to 5.69 kips. That's the first of the three. So now we're solving for X and AY, same thing. The other two equations are summation of force in the X, which is positive A of X, because I assumed it to the right, minus FPDX, which is 5.69 times cosine 50. And A of X becomes 3.66 kips to the right. And summation Fy is A of Y plus 5.69 kips times sine of 50 this time, gives you A of y equals negative 1.11 kips, which is the same thing as 1.11 kips in the downward direction because I assumed it up when I solved my problem. And again, it'll work the same way if you assume the forces to be in the other direction, so it can't go wrong. I like up and to the right just because it makes more sense, kind of like first quadrant. Yes?
Would you also subtract 3.25?
Yes, you would. And we're going to. And somehow the answer still comes out to 1.11. Crazy how that works. So these are your three forces. So now going back to what the problem was. Okay, so before I move on, is everybody good here with just solving for their reactions? Okay. So now we need to actually solve for the shear stress. We're going to need the force acting at A and the cross-sectional area of A. So to get the force at A, you just want the resultant of these two forces. So you're just going to, is everybody cool if I erase the left side just to move the work over? No complaints? So the force that we're acting in A is just the resultant of the two components, because that's essentially what's going on here. That becomes your hypotenuse. So radical 3.66 kips squared plus 1.11 kips squared. I guess technically I could include the negative sign there too, but it gets squared so everything disappears. It's just the magnitude. The force in A is 3.82 kips. People have questions? I hear a lot of murmuring. What's up? So shear force, so parallel, when it says parallel force, what it's referring to, do you see the pin at A, how this pin is going across and you're pulling at it? Parallel force, again, kind of like what I was showing with the marker, would be if you were actually pulling on the length of the pin. But what's happening here is you're still pulling away from it. So what you're thinking of is almost like the third dimension separate from these. So these guys have a pin going through it, and you're using the two reactions to show this guy could be this way, it could be that way, but either way it's pulling at a shear from A. Cool. Any more questions for people on this? Yes.
So the force you use in the equation with the force on area, it's always the force on the pin, smooth, like, it's always going to be that force.
Yes, exactly. So if it was asking for, so yeah, in this case we have a pin at A, so we wanted the force at A. If it was at C, it would be the force at C, but whatever that point is. And then you need the cross-sectional area of that same point.
You can use like that. You always use like 1/4.
Exactly, yeah. Okay, bring it back, guys. Any more questions on what I did here before we get onto that? Yes.
So if they're asking for the normal stress, they would all use the same force?
If they were asking for the normal stress, yes. Then so for this one, the shear force that they gave you can't solve for normal force in this problem because of the way it's drawn and asked. Again, normal stress would be caused by this, so this would have had to have been drawn from a different angle, and they would have had to give you some force here, which we don't know. All we know, if you picture this from the side, you have a force going this way, a force going that way. Those are your shear forces, but they're both pulling away from the pin. None of them are pulling along the pin. That's where you'd be getting into normal force, normal stress. All good? Anybody else? No. Okay. So Okay, bring it back, guys. So the next thing that I want to point out, because this is where you could lose like 1 or 2 points off a little trick, note that it says that the pin is in double shear. So what that means is that it's being pulled, you see here, it's being pulled from both sides. So you have this bar here, that bar there, both pulling on either side of the pin A, which is going horizontally across. So when you get to calculations, if it said that it was in single shear, if it was drawn as if it was in single shear, you use this force as it is, you just plug it right into the stress equation. Since it's in double shear, you're going to take, all you have to do is take this force and divide it by 2. So the actual force you're going to use for the stress calculation is going to be FA divided by 2, which is 3.82 kips divided by 2 is 1.91 kips. So it's a very simple step mathematically, but it's very easy to miss if you don't fully read the question or really pay attention to the way it's drawn. So keep your eye peeled for how that's given. Any questions on that? Cool. And from there, you're going to just plug it into the equation for tau. So your shear stress is equal to your force over your cross-sectional area. The force is the 1.91 kips that it just gave us. And for cross-sectional area, it's a steel pin with a diameter, so we know it's acting like a cylinder, diameter of 3/8 of an inch. So area is pi times d over 2, it's pi r squared. Plug that in, and the shear stress at that point is 17.29 KSI, kips per square inch. And that's the whole problem. Any questions on any part of it? Cool. So is everybody good on topic 2, stress? Awesome. I'll leave that up for a minute in case you guys are still copying, and then we will move on to the last part of it. Fucking lit. Okay, guys, bring it in. Also, one last thing that I forgot I want to touch up on stress before we move on to axial deformation. If the question brings up factor of safety, it might not. Factor of safety is used for design problems where you have some limiting difference between what the maximum allowable force would be. So let's say the problem they gave you, they phrased it differently. They gave you different knowns and asked you to solve for different unknowns, and they told you the maximum allowable stress in the pin is 17.29 KSI, and they told you to solve back for the force maybe. That means that 17.29 KSI is the amount of stress it takes for the thing to actually break. When doing design problems, you don't want to design something right up to the point where it might break, because any little extra thing over that can cause a serious problem, which is why we have factor of safety. So very simply, what factor of safety does is it decreases the force you're using so that so that you have a buffer in between there and the force. So if they say the thing can physically withstand 17.29 KSI and it has a factor of safety of 3, for example, and you back calculated everything and you found that your F was equal to this 1.91 kips, you're going to take that 1 point, and the question was worded as what is the highest amount of force you can design this thing to withstand. You have to say that it can only actually withstand a third of this force. That way you're designed for the safety. This 1.91 kips will essentially break the pin if this is your maximum. So you kind of have to back design it, but just remember that this factor of safety will decrease the force. Is there any questions on that? I don't think they'll give it to you, but just as like a little 2-point curveball he might chuck in there, it's possible.
So basically the same thing as having double shooting for the line force you have by someone.
Exact same. Mathematically, it's the same idea. And then depending on how the question is worded, you could just do the proportion a little differently. But that's it for that. Okay. So the last topic that you have to worry about is axial deformation, which actually just turns into a very simple one equation plug and chug. So the formula is delta equals PL divided by AE, which turns into the deformation in any beam or rod is equal to the force exerted onto that rod times the length divided by the cross-sectional area divided by E, which is Young's modulus. Young's modulus is where you start getting into materials. So steel will have a Young's modulus of something that I don't know. Aluminum will have something else. That will be given to you. You don't need to magically memorize every single material. So just iterate. P is the force in the member. L is the length. A is the cross-sectional area. E is Young's modulus, and delta is the deformation. More often than not, you're going to be solving for delta as opposed to the other way around. So that's the equation. This is a kind of graphically drawn out. Any questions on that? That part's pretty straightforward. So I'll go over problem. Funny enough, my question 3 from last year, which uses this. Okay. So this is the diagram that was given to us. You have beam AC, cables AE and CD, both of which the Young's modulus is given, like I said. Any relevant length, that's pretty much it. So step by step, we'll start to work through the problem. Part A. Draw the free body diagram of ABC, and then solve for the forces. So the free body diagram on this one is very simple. You have force AE. You have force CD. And you have 15 kilonewtons at B. And this is, for those of you who can't see it, this is 2 meters, and this is 4 meters. There's your free body diagram. So you're solving for the forces in the cables. So force AE and force CD. So I started with, I took the moment about A so that this force goes away. So the moment about A is negative 15 kilonewtons times, let's go, negative 15 kilonewtons times 2 meters plus FCD times 6 meters is 0. Solve for force in cable CD, gives you 5 kilonewtons. It was positive 5 kilonewtons since I was drawing it up, so it's 5 kilonewtons up. So that's your first force. And then summation Fy is force of AE minus 15 kilonewtons plus 5 kilonewtons (10 kilonewtons up). Pretty good. Again, just remember to keep these arrows to notate the direction, because if they ask for the vector, they want the magnitude and the direction. They will dock a point if you don't make it very obvious what direction the vector is going in.
That's it for part A, free body diagram and force. Determine the deformations in AE and CD. So now we're getting into the equation for deformation. So part B, deformation in AE is PL divided by AE. So the force in AE, which we just found, is 10 kilonewtons, bless you, times the length, which is both of the cables at a length of 3 meters, given, divided by the cross-sectional area, which diameter of 1 centimeter, so area is pi times 0.01 meter over 2 squared, pi r squared, times Young's modulus, which was given at 175 gigapascals. Plug it into a calculator and you get 2.18 millimeters. Notice how this distance is very small compared to like the length of the rods themselves. You're looking at 3 meters versus 2 millimeters, which makes sense because if you're picturing stretching a bar of steel, it's not going to stretch very much. So use that as a sanity check. If you're getting a deformation that's like feet or meters long, go back and check your work. You probably made a mistake. And then CD is the other one, so we're going to do it the exact same way. Force is 5 kilonewtons times cable length is also 3 meters. Cross-sectional area is the same. As is Young's modulus. Do the math, and it's 1.09 millimeters, which makes sense because the only thing that changed was the force was cut in half, and now our deformation is cut in half. That's it for part B. That's deformation. So that's how you're actually going to use the formula. Does anybody have questions about that part of it? Awesome. Part C, construct a diagram that shows the relationship between these deformations and the deflections at point B. So now I'm going to show you how to actually draw the deformation diagram. And I erased this part on the left over here. Cool. Okay. So with the deformation diagram, what you're essentially doing is you're showing how much displacement each of the points got after the deformation. So the way I've always drawn it, this is your original beam before anything happened, before anything was pulled, say, and this is what you're left with afterwards. So what do we know? We know that, this is A, this is B, this is C, this is 2 meters, and this is 4 meters. We just calculated our deformation. So the deformation in AE is 2.18 millimeters. And the deformation in CD is 1.09 millimeters. Again, this is very much not drawn to scale, but just for the sake of what we're actually showing with this, it's not drawn to. So now you have those lengths. So what I'll do now, so we'll make a triangle here. Because what it's asking for, it wants to see the deflection in B, because then you'll see when you get to part D, it wants you to actually calculate how far B moved. We know how far A moved, we know how far C moved, but now we get to find B, which is somewhere in the middle. So what we do here, so for part B, to get from here to this line is the same 1.09 millimeters. Just for sanity, down here we'll call this A prime, that's the new point, B prime, C prime. This guy moved down 1.9. It moved down more than 1.09 millimeters, but we know this length to start. So the actual displacement of B is this. We also know this distance here, because it is 2.18 minus 1.09, which comes out to 1.09. But these are all values that you could solve for geometrically. So if you look at all the angles, if you look at the sides, you can conceptually figure out what all this is doing. So the last thing that we're actually missing in order to find delta B is this delta X value here. And that's your deformation diagram. So this is everything showing how far B is moved. Anybody have a question about how I draw it, why I drew certain things? Everybody's clear on that? Okay. So now we go to actually solving for B. At this point, we're just doing, it just comes out to a proportion. So you look at this triangle, you get 4 meters over delta X equals 6 meters over 1.09 millimeters. Remember to convert that to meters when you actually do your math. X is 0.727 millimeters when you actually solve the proportion. So this delta X is that. And then the amount that B actually traveled is the 1.09, which we see geometrically here, plus that extra 0.727 millimeters is 1.817 millimeters, and that's the displacement of B. Any questions? That was the whole problem. Okay. So that was my entire test. That's everything I had prepared. Just as like a fun little thing, Someone had mentioned something casually to me about strain. Strain has never been on a test for as long as I've seen any of these. Just for fun, do a different color just to clear it out. Strain is equal to the deformation over the length. So if you plugged into delta equals PL over AE, and they ask you to find strain as the last step, it's delta over L. I highly doubt they're going to. That being said, that's it. Does anyone have any questions on anything?